Hi, I'm John Aynsley from Doulos. I'm going to give you an introduction to UVM, the Universal Verification Methodology. So what is UVM? Well, UVM is a methodology for writing test benches for a design that could be in Verilog, VHDL, even SystemC. UVM itself is written in SystemVerilog. So one of the main deliverables in UVM is the UVM Base Class Library, or BCL, yet another three-letter abbreviation for you to remember. UVM supports constrained random verification. So because constrained random verification is central to UVM, I'm going to spend just a couple of minutes telling you about it. Constrained random verification is the idea of using random vectors in simulation. Simulation is still the workhorse for functional verification today, and over the last few years constrained random verification has come to represent a state of the art in how best to use simulation. So the idea is to randomize at least some element of the test vectors that you throw at your design during simulation. And there's two key benefits from randomizing test vectors. The first really fundamental benefit is that constrained random simulation is great for finding unexpected bugs. I mean, just think about it. If you have to plan up front the individual noughts and ones that you're going to throw at your design, you're only going to find bugs that you're really looking for. The idea with constrained random verification is to scramble, randomize the test vectors, and that way you push the design into states you just never thought of. The other key benefit is automating stimulus generation. And the point about automation is that you can run long simulations. You can run simulations overnight or over a weekend on a server farm without having to manually write all those test vectors yourself. They can be generated automatically. So how does constrained random verification work? Well, I always remember this as the 3 C's of constrained random verification. That is, checkers, coverage and constraints. So if you've got random vectors, it's critical that you automate checking, that you write self-checking test benches in SystemVerilog. So the inclusion of checkers is the first of the 3 C's. Knowing does the design work. Then comes the second of the 3 C's, coverage, which is answering the question, are we done yet? So functional coverage is about recording what goes on during a verification run and identifying how thoroughly we've exercised the design. So what do you do if you have coverage holes, if you haven't exercised the design thoroughly enough? Well, that brings us to the third of the 3 C's, which is constraints. We need to be able to constrain those random vectors in order to increase test coverage. So UVM is a methodology built in SystemVerilog for doing constrained random verification. UVM is an industry standard. It was developed by Accelera, the standards body of the EDA industry, and it includes a lot of big names in its development, including Cadence Mentor Synopsys, and also a number of other big electronic systems businesses. I've just highlighted a few of those on this slide. The guys on the left-hand side are key here because Cadence Mentor and Synopsys not only offer political support for UVM, they also offer technical support in terms of their simulators. So right now UVM runs out of the box on Cadence Mentor and Synopsys simulators. UVM is pure SystemVerilog code, no hacks in there. It's open source, comes with an Apache license, so you can take the source code and do pretty much what you like with it. It has comprehensive documentation, so it comes complete with a reference manual and a user guide. And here on the slide you can see the URL for downloading UVM, or at least as it was at the date when I created this video. So how does UVM relate to other standard methodologies? Well, UVM is directly based on OVM version 2.1.1 in fact, and it also draws a number of ideas from VMM. UVM's very close to being backward compatible with OVM and also is near backward compatible with the early adopter version of UVM. Personally, I've ported quite a bit of code from OVM and UVM early adopter now into UVM, and it's possible, it's not a big deal. So your vendors are going to continue to support OVM and VMM for the time being, but it looks like the industry now is going to converge on UVM over in the long term. So now I'm going to have a look at some of the key technical highlights of UVM, just to give you a flavour. If you want to have a look at some other technical highlights, then have a look at the 10 things you should know about OVM video as well. Obviously that's about OVM rather than UVM, but there's a lot in common. So let's start with stimulus, generating test vectors. UVM features a layered approach to generating test vectors using so-called sequences. So a sequence generates transactions, and a sequence is also an object that can be manipulated. So a sequence is both a function and an object, a so-called function object. Sequences can be built up out of other sequences to have a hierarchical structure or a layered structure. So you can actually end up with a layered structure of sequences, mirroring the protocol stack in your design. And then as sequences get instantiated, they can be overridden and controlled top-down in order to constrain precisely the set of test vectors that get generated. Let's have a look at the big picture of how UVM hangs together. So one of the big themes here is verification reuse, reusing verification IP. So a test bench for a design under test would typically be built out of verification components. Those verification components you could build from scratch, or you might reuse them from previous projects, or go out and try and buy them. So UVM offers a standardized, consistent structure for building verification components. One of those standard structures is known as the UVM agent. An agent consists of a sequencer that generates sequences. Those sequences generate transactions that are passed down into drivers. The driver wiggles pins on the design under test, and a monitor watches the interface to the design under test, extracts transactions, and then sends those transactions off to the rest of the verification environment. So consistency and not reinventing the wheel is an important element of UVM. The UVM component then gets reused as part of a bigger verification environment, and as it's reused it can be configured to the precise needs of that verification environment. So one of the big highlights of UVM is the ability to reconfigure components without needing to go in and hack the source code of those components. The verification environment would contain a number of, again, a standardized structure, including components such as virtual sequencers. A virtual sequencer is a component that coordinates the activity of other sequencers. And scoreboards. The scoreboard is a component for doing things like functional coverage and checking. Then the overall verification environment is reused according to the demands of specific tests. So one of the features of UVM is separating tests from the rest of the reusable verification environment. And again, the same kind of configuration mechanism can be applied to reuse the verification component for the verification environment for individual tests. There's a couple of ways to do that. One is known as the resource database. That's a general way for reusing resources between UVM components. So we've looked at how we can structure the verification environment into different kinds of verification components. There's also a standardized set of execution phases in UVM. So things start from the build phase. The build phase builds the hierarchical structure of components. Then the connect phase, which connects together ports on those components. So the build and connect together are a bit like elaboration in VHDL or Verilog, if you're familiar with that. Then come a couple of housekeeping phases, end of elaboration, start of simulation, which happen to be the same name as is used in SystemC for those same phases. Then we get on to the run phase, when the dynamic things happen, sequences execute. And then after the run phase, there's a number of housekeeping phases to tidy things up, extract, check, report, and then final. So a few other features. UVM also supports transaction-level communication, which was borrowed from SystemC, message reporting, an end-of-test mechanism, also known as objections. So each component raises an objection when it's finished, when it's busy, and drops that objection when it's finished. And then finally a register layer, which was borrowed from the VMM RAL, or register abstraction layer. So at Doulos, we can also help you by delivering training classes. We offer a range of training classes, including classes in SystemVerilog and UVM. If you want to know any more, you can find details from our website at www.doulos.com.